Hello listener, my name is René. I am a PhD student at the German Research Center for Artificial Intelligence, and I'm going to present our paper about SSGP, a deep neural network for very robust interpolation of all kinds of tasks. Sparse dense interpolation in computer vision finds its application in many problems. Most important for me personally is the densification of motion and depth, since I work with scene flow. The advantage of the concept is in all cases that sparse estimates can be obtained in areas where this is comparatively easy or cheap. The interpolation then takes care of the remaining areas to still get a dense result. The biggest driver for these kinds of algorithms is the densification of sparse LiDAR measurements into a dense depth map with respect to a reference image. While our method is inspired by depth completion, we present a deep architecture that can perform the interpolation for a variety of problems equally well. Also, SSGP is designed to be very robust against noise and changes in the density distribution of the input. This is achieved by a set of architectural concepts. Firstly, the core is a denoising autoencoder, where gaps in the input can be also considered as a severe kind of noise. Furthermore, the interpolation, or rather extrapolation, is modeled as spatial propagation of known pixels into their neighborhood. Additionally, image guidance is implemented by predicting spatially varying propagation kernels based on the image, since the image contains the important information of the scene, like the geometry and interpolation boundaries. Compared to previous work, we predict a single set of shared propagation kernels for all feature channels, which reduces the computational complexity and the memory footprint of our model a lot. Lastly, the network is explicitly equipped with awareness of sparsity by using normalized convolution and sparse average pooling. Here, a sparsity mask is considered during propagation to avoid the mixture of invalid and valid information. All combined, this leads to our sparse spatial guided propagation, in short SSGP. Training details for the network are given in the paper, and there we also conduct an ablation study to measure the impact of the design components. Now let's see how robust SSGP is. This diagram shows the increase in an error metric for scene flow when adding additive Gaussian noise to the sparse input. The competing methods have doubled the error at about a standard deviation of 3 pixels. SSGP maintains its accuracy even for heavy noise with almost no degradation at all. In a second experiment, robustness against the density of the input is tested. The dashed lines show results for depth completion of SSGP and the network that represents state-of-the-art. The solid lines are again scene flow results. In both cases, SSGP shows a superior robustness compared to previous work. For scene flow, the performance starts to drop only after removing 99% of the input. We have also experimented with density distribution of the input and could observe a similar result. This validates that the interpolation network is very robust. To give a qualitative impression of the interpolation results, this slide shows the visualization for a sparse to dense optical flow estimate on a sample from the KITTI dataset. This example shows dense predictions and the corresponding error maps for 4 methods, including our SSGP. It can be seen that SSGP predicts consistent areas with very sharp and accurate object boundaries. And interestingly, the image guidance of our network is able to distinguish between object and shadow, a common source of errors for other approaches. Quantitative results for all interpolation tasks and more datasets are given in the paper, where it is validated that SSGP is suitable for a broad range of applications. For discussion, please join our question and answer session or contact me directly. Thank you and have a nice day.